Good morning, friends. The next unit is design of shear walls. A shear wall is a vertical wall which have been designed to resist lateral forces resulting from wind and earthquakes. Generally, it is made of concrete or brick. It is normally provided between staircase, columns, lift wells, toilets, utility shafts, etc. And normally, it has been suggested in tall buildings for lateral load resisting element as lateral load resisting element, and normally buildings with flat slabs are always suggested with shear walls. We need to ensure that the bending tensile stresses resulting due to lateral loads are minimized or reduced. So this can be done using gravity load application on the wall. So the shear wall is designed for taking gravity as well as the lateral load, the bending tensile stresses resulting from the lateral loads can be reduced. We need to ensure that we place the shear walls symmetrically so that we avoid torsional stresses. Shear walls which have been used for resisting earthquake forces have to be designed for ductility. This is a picture of a shear wall. We can see that walls have been placed symmetrically in both the orthogonal axes in plan. Placing of shear walls. Um, the most difficult task in positioning a shear wall. So we need to ensure that the eccentricity created in the plan, that the plan eccentricity is very minimum, so that the torsional stresses can be minimized or can be avoided. So we need to ensure that we always place shear walls in symmetry in the plan axis, and we need to ensure that we provide shear walls in both the orthogonal axis so that uh, shears resulting from x as well as y directions are resisted. Shear wall is so strong in plane action, whereas out of plane action it is a very weak member. So we need to ensure that shear walls are put in both 90 degrees so that shears in orthogonal axis are resisted. Shapes, it can be of any shape, and what we use normally is like the hollow core, which we use it for elevator shafts. Other common shapes are channel shape, L shaped, simple rectangle. These are the shapes that we use commonly. And this is the picture depicting the reinforcement detailing of a shear wall, which is nothing but a double mesh. Depending upon the thickness of the wall, the reinforcement can be provided in double layer or in single layers. And when the edges are not sufficient to take the allowable compressive stress, so we need to add stiffened edges, which are nothing but boundary elements. So these boundary elements can be of the same thickness as of the wall, or it can be enlarged ends. So normally what we do is like we place shear walls between columns, so those columns act as the boundary elements or the stiffened edges. Classifications of shear wall. Shear walls can be classified into the following types: a simple rectangular wall, flanged wall, coupled shear walls, rigid frame shear walls, framed walls with infill frames, column supported shear walls, core type shear walls. Classification of shear walls. Those have been displayed in pictures. The first one represents a simple rectangular shear wall. B represents flanged walls. That is nothing but we have column or we have some boundary elements which acts as flanges. And the third one is the coupled shear wall. D represents framed shear wall, and then column supported shear walls, and then core type shear walls. Simple rectangular type and flanged walls. Simple rectangular is just a rectangular in plan, and whereas the flanged one we have barbell type normally which we use it. Those act as boundary elements placed between columns. This resists in-plane vertical and horizontal forces and are subjected to shear and bending. So shear and bending forces are developed in a shear wall. In simple shear walls, that is rectangular shear walls, steel is uniformly distributed. Whereas in case of a barbell type, barbell is like two edges are enlarged. So minimum steel is provided in the web part, and boundary elements are the stiffened parts. So the remaining steel is provided in the boundary elements. These barbell walls have better ductility. Normally, these walls should be designed for failing in bending rather than shear. And normally these shear walls attracts more forces as they are very rigid and dissipate energy through cracking. So cracking once appear, it is really difficult to repair. Coupled shear walls, when two walls are jointed using uh, beams, short span beams, which were call it as spandrel beams or coupling beams, it is called as a coupled shear wall. So this results in increased stiffness of the walls, and it dissipates more energy by yielding of spandrel beams, whereas the walls remain undamaged. So we need to ensure that hinges are developed in the beam before shear failure, and so that we need to design the coupling beam to have good energy dissipation characteristics, and these beams are displaced vertically under lateral loads and have double curvature in under bending. So if we need to find out the reaction or the vertical axial force acting on the shear wall, it is given by this equation where MP represents the plastic moment of the beam and LB represents the length of the spandrel beam. And since these spandrel beams fail in shear rather than bending because of short spans, we need to see that it has been designed for shear. So in order to have additional shear resistance, we provide diagonal steel in spandrel beams. This is a picture depicting the action of coupled shear walls, how the coupled shear walls act. And this is the diagonal action, strut action appears. So we need to ensure that we provide reinforcement along the diagonal so that it resists those shears developed. Rigid frame shear walls. These are combination of rigid frames and shear walls. So the deflection of the frame is in shear mode, and whereas the deflection of the wall is in bending. So the interaction reduces the moments, but it also increases the shears in the shear walls. So the shear walls have to be designed to take this increased shear. Framed walls with infill frames. Framed walls are nothing but where we have beam column arrangement as well as the shear walls are being built in monolithic construction. And in case of infilled frames, where the frames have been constructed first, later on the shear wall, it can be of a brick or masonry or blocks, those are filled, and these have been designed to resist lateral forces. Column supported shear walls, whenever we need to have a big opening kind of thing, then we need to have ensure that the shear wall goes up to the foundation. So what we do is like we go for columns to transfer the forces from the shear wall to the foundation. So this becomes a column supported shear wall, and because of this discontinuity happens, and vertical irregularity happens in the structure. So we need to ensure that the structure has been designed to to counter the irregularity and to have proper ductility. Core type shear walls. These are the common kind which we use it in elevators and utility shafts. Unsymmetrical positioning always leads to twisting, so same thing applies here. So if twistings are absent, it acts like a simple shear wall. The advantage is that it has shear walls in both the orthogonal axes, and the lintels which are acting as beams in lift shaft kind of thing has good resistance to torsion. Classification according to behavior, shear walls, simple shear walls. So these or deflection and strength controlled by shear, where shear becomes the major force and resisting the lateral forces by shear development. These can be used in low-rise buildings. Ordinary moment shear wall, where deflection and bending comes into picture. So flexure is the major behavior rather than shear. These have been used for high-rise shear wall, high-rise buildings where wind and cyclones are the major lateral forces. Ductile moment shear wall. These are used for seismic resistant buildings, and these have to be designed for good energy dissipation as well under reverse cyclic loadings. So ductility comes into picture here. So we need to go for ductile detailing. Some of the terms which we'll be using on lateral stiffness, the force required to be applied at its top in order to produce a unit displacement. Center of rigidity, the point on the horizontal plane through which the lateral load should pass through in order that there will be no rigid body action. In simple terms, the point at which the resultant of the restoring forces of the system acts. Center of rigidity and center of mass are calculated in plan. Center of mass, the point at which the entire mass of the system is concentrated. These are given by these simple equations which we use it for calculating center of gravity of a shape. Now, center of rigidity and center of mass have to coincide so that torsion doesn't appear in the structure. And, our seismic code IS 1893 suggests that we need to design for a minimum accidental eccentricity of 0.0. That's like 5% accidental eccentricity is allowed. In case the eccentricity exceeds, torsion will be created. Torsion stresses will be arising. So we need to design for them. Principles of shear walls. Normally, we assume that all lateral forces are resisted by shear walls with no participation from frames. So without torsion, the load taken by each wall is proportional to its stiffness. So it is the force on each wall is given by this final equation. The stiffness of that wall upon the summation of stiffnesses of the walls at that level into the lateral force. So we result in the force of that particular shear wall. Stiffness, how to calculate stiffness? So stiffness in a shear wall arises due to bending, shear and rotation of foundation, or we call it as rocking on foundation. So these are given by these three simple equations, and then the total deflection becomes summation of bending, deflection in bending, shear and rocking on foundation. The lateral stiffness is given by W upon the delta, load upon the stiffness, load upon the deflection. Design last steps for rectangular shear walls. First step is to like general dimensions, where we decide the thickness of the wall and the length of the wall. Normally we go for column to column so that the specified length can be maintained easily with no openings or with openings. And thickness, there's no rule as such to fix some thickness. So it's normally we go for thickness of the wall, brickwork kind of thing. So we can go for 200 or 230, 250 mm thick, which will be enough for resisting. The shear strength, horizontal and vertical reinforcements. So what we do is like we arrange steel, or we calculate the minimum steel required for a wall, and we arrange them in both vertical and horizontal ways, so it becomes mesh. So this mesh can be provided on single side as a center, or it can be a double mesh placed on both faces. So that depends upon the thickness as well as the shear stress developed on that wall. And with that shear strength requirement, we need to check for boundary elements, whether the given thickness and length is it okay for having without boundary element, or whether we need to go for a boundary element. So depending upon that, we need to go for boundary elements, and then we calculate uh, the actual shear strength requirement. So whether the minimum steel will be able to provide the shear requirements, or we need to have go for additional shears. And then flexural strength of the web, we cannot we are not determining flexural strength of the column part or the boundary element. So what we do is like we calculate the flexural strength of the bone of the web part, that is central part, and so that the force on boundary elements can be calculated. So after that, design of boundary elements are designed as short columns with the axial loads. So as per IS 456, we do the design as per for a column. And then calculation of development length and anchorage. And in case we are having openings, then openings should have some additional reinforcement, so that has to be calculated. And any discontinuity in walls, so that has to be detailed properly. And then shear strength in construction joints. Now effectively we will be stopping up to flexural strength for design purpose in examination. Now these are the total provisions given in IS 13920 1993 version. So thickness, we need to see that the thickness of shear wall is not less than 150 mm, and people normally go for maximum of 400 mm. And in flanged wall, the effective extension of the flange beyond the face of web is given by half the distance to an adjacent shear wall web, or one tenth of the total wall height or the actual width. And extreme fiber compressive stresses due to all loads exceed zero point 0.2 FCK, boundary elements are to be provided along the edges. So especially enlarged and strengthened by longitudinal and transverse reinforcement as in columns. And these boundary elements can be discontinued when the stresses uh, are less than 0.15 FCK. Vertical and horizontal reinforcements. We need to provide reinforcement in two orthogonal directions in the plane of the wall. So minimum steel required will be 0.25 percentage of the gross cross-sectional area, and when shear stress exceeds 0.25 FCK or thickness is greater than 200 mm, we need to provide in steel in both phases, that is like in two mats. And diameter of the bar to be used shall not be greater than one tenth of the wall thickness, and maximum spacing shall not be greater than L by 5, where L is the length of the web, reducing the thickness of boundary elements, or 3 times the thickness of the wall, or 450 mm, whichever is minimum. Vertical steel provided for shear wall shall not be less than the horizontal steel. Shear strength calculations. So we provide reinforcement from minimum, so horizontal as well as the longitudinal reinforcement. And what we do is like we calculate the shear stress, and we need to see that whether the provided steel is enough, okay or not. Now tau v is actual shear stress, so it is given by vu upon td. So d is the effective width, so 0.8 for shear walls. And calculate tau c and tau v, and tau v should not exceed tau c max. And then we calculate that additional shear, that is tau v minus tau c into td, and that's very similar to our beam calculation. And then arrangement of steel. And in case of boundary elements, what we do is like gravity loads So the total axial load acting on the boundary element. Boundary element is nothing but a short column, designed as a short column. So gravity loads that come to that part, so that we calculate as per the proportion of that area, plus or minus. It can be actually a couple is created, so it will be like plus and minus. So mu minus muv. Mu is the total moment resulting from the loads, and the muv is the capacity of the web, moment of resistance of the web upon c. C is the center to the center distance between the boundary elements. Flexural strength. These are the equations that have been taken from IS 13920 Annexure A. Two cases are there when x by L is less than xb by L, and other cases like x by L is greater than xb by L. Example 1. Design a simple shear wall of length 4.16 meters and thickness 250 mm, subject to the following forces as given in the table. Use M25 grade concrete and Fe415 grade steel. The wall is a high wall. So where the length of the height of the wall doesn't come into picture here. Dead load plus imposed load, those have like axial load of 1950 kilonewtons, moment of 600 kilonewton meter, and shear force of 20. Seismic load 250 kilonewton axial load, 4800 kilonewton meter as moment on the shear wall, and 700 kilonewtons as shear force. So in this case we need to uh, actually the thing is like they have given for separate load cases, they haven't given for the load combinations. Then we need to go for the load combinations as prescribed in table 18 of IS 456. So table 18 which gives like we'll be going for the worst one since we are doing manual, so we'll not be calculating for each and every load case. So normally as per table 18, when lateral loads and imposed loads are acting on, so these two criteria will be acting on 0.9 times dead load plus 1.2 times 1.5 times earthquake load, and 1.2 times dead load plus live load plus 1.2 times earthquake load. So this two will be the governing cases uh, which have been taken from table 18 of IS 456, the class 9.4.3 of IS 13920. Now 0 0.9 times dead load, so we reduce it to 0.8. That comes from IS 13920 class 9.4. In that one, like when the gravity loads are used for resisting the lateral forces, then we can reduce the factor from zero point 0.9 to zero point 0.8. So these are the final forces from the load combinations. In case 1, 0.8 times dead load plus 1.2 times earthquake load. So what we get is 1860 kilonewtons. Now this will be used for getting maximum uplift. And case 2, so where axial load is 2640 kilonewtons, moment is 6480 kilonewton meter, and shear is 864 kilonewtons. Then we need to check the boundary element. So for that we need to calculate the bending tensile stresses. So we need to calculate the moment of inertia and the cross-sectional area. Moment of inertia BD cube by 12. So where B represents the thickness, so 250 mm, and D will be the depth of the wall. Now initially we are taking it as a rectangular wall with no boundary element. We need to check the compressive stresses there. So bending compressive stresses. So 4160 will be the depth. So we get this I value 1.5 into 10 power 12 mm4, and A B into D, so 1.04 into 10 power 6 mm square. Bending tensile stress, bending stresses given by P by A upon M by Z, and so we result in the maximum as 11.52 Newton per mm square and minimum as minus 6.45 Newton per mm square. So now, to avoid a boundary element, we need to see that um, the bending stress is less than zero point 0.2 FCK. So zero point 0.2 into 25, 25 is the grid of concrete which we are using on. So it should be less than 5, but actually we are having greater than 5 in both the cases, maximum as well as minimum. So we are bothered about compressive stresses. So we have to go for boundary elements, and here we assume a column size. This is an assumption. So if it is unsafe, then we need to revise it. The assumption is that we are providing a column or an enlarged end of size 500 by 500 mm at both the edges, and so the length of the central part or the web part will be 3610. So 500 goes at each edge. We have been left with 3610 mm. Next one is to provide steel. So steel, we need to check whether it has to be provided in a single layer at the center or in two layers, one at each face. So that criteria has been given by the shear stress if it is not exceeding 0.25 fck or the thickness is exceeding 200 mm. So here we calculate the shear stress. So the first shear was 864 kilonewtons. So, and we need to consider for shear resisting the center to center distance between the boundary elements. So 3610 plus 500 by 2, 500 by 2. So we get 3660 mm. So this results in 0.94 Newton per mm square, and limiting is 1.25, and so it is safe. But whereas the thickness is exceeding 200 mm, so we need to provide steel in two layers, that is one at each face. Steel required, so we go for the minimum steel initially. So 0.0025 into Ag. These are taken from class 9.4 from IS 13920. So we end up in 625 mm square. That is both phases together. So this steel has to be provided uh, in two phases. So divided by 2. So we result in 313 mm square. And assuming 10 mm bars. Maximum bar diameter of the bar to be used is thickness by 10. So we have 250 by 10, 25. So we have taken as 10 mm bars. So we are on safer side. So spacing required is 251 mm. So we'll be providing at a spacing of 250 mm. And maximum spacing. So minimum of length of web by 5 or 3 times the thickness of the wall or 450 mm. So in this case 450 mm is the governing one. So and still this bar spacing calculated is 250. So 250 is the spacing provided. So we'll be providing 10 mm bars spaced at 250 mm center to center on both faces vertically and horizontally. So that means we are providing the same amount of steel longitudinally as well as transversely. So AST provided is approximately 628 mm square, and PT remains the same, almost 0.25. Shear check. So we need to calculate the shear taken by steel. So PT provided is 0.25, and the tau c by the concrete is 0.36 Newton per mm square. This has been taken from table 19 of IS 456, and tau c max 3.1 Newton per mm square. This value has been taken from IS 456 table 20. So we need to see that tau v doesn't exceed tau c max, and tau v, if it exceeds tau c, then will be providing shear reinforcement. Now, that additional shear, which we use the same thing from limit state of shear, uh, ultimate limit state shear. So V is tau c equal to tau v minus tau c into BD. So tau v is 0.94 Newton per mm square, which we have calculated earlier, and 0.36 is the allowable shear stress into the thickness 250 into 1000. So here we are not multiplying by the entire length of the wall, rather than per meter we are calculating. So it results in 145 kilonewtons, and we calculate uh, a factor called ASV by ASV, that is area of steel required per meter. So we calculate it from this equation, which is given from IS 456 um, 2000. VUS equal to 0.87 FI. A is V D upon SV, where Fi represents the grade of steel, ASV represents the area of steel in vertical, that is the shear reinforcement, and D represents the thickness of the wall here, and SV represents the space. VUS is the unbalanced shear. From this equation, we calculate ASV upon SV, so which results in zero point 0.4. So required is zero point 0.4. We need to ensure that provided it should be greater than this. So provided is like yeah, provided steel is 628 square mm divided up by 1000, so we result in 0.628. So that means the minimum steel provided satisfies the shear requirements. Now everything is calculated. The next step is to calculate the flexural capacity of web, so that we'll be able to calculate the axial load coming onto the boundary element. Or in simple terms, the flexural, if we are not going for a boundary element, the flexural capacity of the shear wall should be greater than the moment resulting from the loads. Now in this case, since we have a boundary element, two boundary elements, one at each edge, so we need to see that um, either web can be exceeding the stresses, or it can also be less than the moment, so that the additional forces are to be taken by the boundary elements. Now we calculated based on these things from equations given by IS 13920 annexure A. So first is the uh, axial load calculation, which we need PU. So we take it for the minimum, so we are going for minimum axial load and maximum moment, so that we end up in the minimum capacity, or in the worst criteria, so that the wall is safe under all proportions, or under all categories. So load on web, we calculate it by the proportion. So web area upon the total area of the wall into the load. So we end up in 1139 kilonewtons. The total load is 1860 kilonewtons, and the web area is web length is 3160 mm, and thickness is 250. And whereas boundary elements are 500 by 500, so into 2, so we get the total area, and by this proportion we get the load on web is 1139 kilonewtons, and from this one we calculate lamella, pi, and beta. And here calculating lamella, PU represents the axial load on web, FCK the grade of concrete, TW represents the thickness of web, which is 250 mm, and LW represents the length of the web, which is 3160 mm. So this lamella works out to 0.0576, and pi 0.87 Fi rho upon FCK. Fi is 415 grade steel, and rho is the PT provided, that's the percentage of steel provided. FCK is the grade of concrete. So pi works out to be 0.036. Beta 0.87 Fi upon 0.0035 ES. ES represents the Young's modulus value of steel, 2 into 10 power 5 Newton per mm square, and beta works out to be 0.515. Now using this, we calculate XU upon LW, that's the length of the web. So from this proportions we get XU upon LW is 0.216. We need to compare it with XU star upon LW. So this is given by this equation, and these equations have been copied from IS 13920 1993. And XU by L, XU star by LW works out to 0.66. So the first equation is satisfied. XU upon LW is less than XU star upon LW. Now this is the equation, such a big equation. And finally, when you solve it, we get the moment of resistance of the part to be 2371 kilonewton meter against 6480 kilonewton meter. So that means the rest of the moments are to be taken by the boundary elements. Boundary elements are acting as a couple. One is in tension, the other is in compression. So the force on boundary elements. This equation is given in our code 13920. So the difference in moment upon the center to center distance between the boundary element gives us the equivalent axial load on resulting from the moment. So this is given by 6480 minus 2371 kilonewtons, so 4109 kilonewton meter upon the center to center distance, so which works out to be 3.66 meter. So the equivalent axial load on the boundary element comes to 1122.5 kilonewtons. Now this is the load coming from moment, and apart from that we have vertical loads. So the total compression load acting on the boundary element will be in this case we need to consider the maximum compression. So, and again, how to calculate is like by the proportion. So the total vertical load is 2640 kilonewtons. So 2640 into area of boundary element upon the total area of the wall, so which works out to be 512 kilonewtons. And for tension or the uplift, so we need to take the minimum uplift load. So that comes out from case 1, 1860 into that same way, so it comes out to 360. So finally the boundary element has to be designed in compression for 1122 plus 512. So that comes around 1635 kilonewtons, and a tension of 1123 minus 360. So these boundary elements are to be designed as short columns, where will be resulting in 4 number of 12 mm bars or 16 mm bars, and then we need to provide lateral ties in form of shear links, shear loops, and we call them as confinement reinforcement. So with that, the design of shear walls come to an end. These are the references. Thank you.